Hello. We have seen four simulation results of different types of dice, and the result was surprising. When you increase the sample size, the probability of the average, the distribution of the average, converges to the same shape, no matter what the how the dice looks like, how what is the no matter what the original distribution is. So we are going to formulate the results. First property, first property is about the expectation. So the expectation of the average is the same as the expectation of a single dice. As I explained, the center does not change. It is always centered at the same point, no matter what, no matter how many dice you throw. So it's easy to prove, like for example, when you have two dice, we know by the assumption of a random sampling, the first expectation and the second expectation is the same. Then the expectation of the average equals the expectation of the definition of the average, x1 plus x2 divided by 2. And then 1 over 2 goes out of the expectation, and you can split expectation for x1 and x2 in this form. And it's half of x1 expectation plus x2 expectation, which happen to be the same, so it cancels out. So in the end, it's just one expectation. So single outcomes expectation equals to the expectation of uh, the average of many numbers, and it doesn't matter how many sample size you consider. Regardless of the sample size, the mean does not change. That's property one. It's nice, very simple. And property two says the variance and the standard deviation depends on the sample size n. In particular, the variance of the average is the original variance. This is the variance of a single outcome divided by the sample size. And which automatically implies if you take square root on both sides, you obtain the standard deviation. So the standard deviation of the average is the original standard deviation divided by square root of sample size, right? So if you accept the first one by taking square root on both sides, you obtain the second one. So it means that as the sample size increases, the variance or the standard deviation decreases, right? So they are inversely proportional to the sample size. Its proof is also simple. Same, like variance of the average is can be written in this way. This is the average, and the major difference from the earlier proof is that when you multiply 1 over 2, when you divide by 2, to get this out of the variance formula, you have to square that. You remember, like linear transformation to something is not preserved by the variance. So when you multiply a, the variance is multiplied by a squared. So when you divide by 2, the variance is divided by 2 squared, which is 4, but there are two variances, so one of them is cancelled out. So in the end, you only have one in the denominator, that is n. So in this example is for two observations, so denominator has 2. If you consider 3, then you will have 3. If you consider n, then you will have n here, right? So anyhow, the point is you don't need to know the proof. The point is the variance is the original variance divided by the sample size, right? And the last property, the distribution of x bar, the sampling distribution, converges to a normal distribution as n increases. So When n is small, it does not look much like a bell curve, but when n increases, it's very much like a bell curve. So this is a very wonderful, it's a great, powerful, surprising result because it says the distribution of the average is normal no matter what the original distribution is. So we have considered many different starting points, many different distributions for a single dice, but in all cases, they converge to a normal distribution. So the distribution for a single observation is not normal. It doesn't need to be a normal distribution, or it can be actually any distribution. So still the property holds. That means even if you don't know the distribution of a single dice, you know the result. Still, even if you don't know how the dice looks like, still you can predict the distribution of their averages. So no matter what the dice looks like, if you throw 25 dice, it's the distribution of their average is going to be a normal distribution. That's the power of this property. So this is why in the previous chapter I explained that you are going to use normal distribution and only using normal distribution from now on. This is the reason. No matter what the distribution is, it's going to be normal distribution in the end. So you don't need to know any other distribution. So that's why this chapter is important, and why normal distribution is important. So let me combine them using, we learned three properties, and there are different names for them. First, you may have heard about this, the law of large numbers. The law of large numbers say it combines the first two properties. First property says no matter what the sample size is, the expectation is the original expectation. The original expectation is the same for all sample size. And the second property says the variance of the average decreases as sample size increases, and in the end it will be zero when n increases to the infinity. Then combining these two means, so first observe this. In the limit, the variance of the average is zero, which means x bar, the average is not random. Its variance is zero. So randomness in x bar, the average, disappears as n goes to infinity. In the limit, the randomness disappears and always x bar converges to x, the original expectation of x, right? So the sampling distribution becomes more and more concentrated, and in the end it will be just 1 point. In the end, x bar, the average, equals to the true mean with 100%. There is no more randomness. That's the law of large numbers, right? And the second theorem, and the most important theorem in statistics, is the central limit theorem. The central limit theorem says for sufficiently large n, when n is sufficiently large, x bar, the average, follows a normal distribution with these parameters. By the way, here you have to have, this is the mean and this is the variance. The mean and the variance are from these two guys, right? The mean of the expectation of the average equals to the original expectation, the original mean, and the variance of the average equals to the original variance divided by n. Using these two outcomes, we have normal distribution parameters. So not only normal distribution, but also we know their parameters. So then, typical question here is, so this is the central limit theorem. and it says no matter what the original distribution is, we know the distribution of x bar. It's a, isn't it surprising? It's a very powerful theorem. So then the question is, how large is sufficiently large? How can you say it doesn't sound like a mathematical term, but uh, it means it's converging to a normal distribution. So it's always an approximation. It cannot be 100% correct. It's an approximation and going to the limit. But in textbooks, the threshold is usually set at 30 or 35. So if your sample size is 30 or 35, then you may approximate the distribution, the sampling distribution, to a normal distribution. But this is just a bare minimum, like 35. These days, in the era, like in the big data age, 35 is nothing. So, at least I would recommend you to have like more than 100 observations to do any kind of analysis. These days, like several thousand, several like million data are not that rare. So, uh, and as the sample size increases, this theorem becomes more and more powerful because the larger n is, the more accurate the approximation is. So this is an approximation now. Now it's just it. Excuse me. It looks like a bell curve, but not exactly a bell curve. But when n increases, it's getting closer to a bell curve. So it's the approximation becomes more accurate. So this is the most important theorem. And to summarize, no matter what the single outcomes distribution is, we know that the sampling distribution is a normal distribution, and the parameters are given by the original mean and the original variance, the mean of a single observation and the variance of a single observation. So if you know, so we need three conditions. If you know the mean of a single observation, and if you know the variance of a single observation, and if you have sufficiently large sample size, under these three assumptions, you know everything about the sampling distribution. That's what this theorem says. So we are going to use this result to think about an example in the next video. So yeah, see you in the next video. I'm going to continue with a new example.